Hello, everybody. We are still talking about the Fick's law and the molar flux, and we want to see or find an answer to this question, which is why is Fick's law used to calculate the molar flux relative to the average flux or the average velocity, and it's not only calculating the absolute flux, the molar flux. To answer this question, we need to think more about the case of diffusion. So let's say we have a system like the one we see here. There is one species that has high concentration on the left hand side and it has very low concentration on the right hand side. Let's say it's just a perfume that you have sprayed in part of the room and it's diffusing into the other part of the room. In the beginning there is no concentration on the other side, but it's higher concentration on your side. And as we see, there is a very clear concentration. I'm sorry. There is a very clear concentration difference between here and here, which is very obvious and clear. And this is not only what we have. So the concentration difference leads to something else, which is due to the mixing of the two species here, which makes or creates a difference in density between this area or this place and this place. So you can think of it like if you have water or pure water and another cup that has water and alcohol, for instance. So the density of water would definitely be different from the density of water and alcohol because you have a mixture, and this mixture will have an average density that is average between that of water and that of alcohol. So this is the same here. You have two components here that have two different properties, and then the mixture that you have of the two species will have different density than the density of the pure component or the mixture on the other side that has lower concentration of species A. And this is what happens. And these two differences that we see here will be or will lead to two different driving forces. So one is the first concentration difference. We know that this is kind of something that we talked about many times before, that the concentration difference will lead to diffusion motion from the left hand side to the right hand side for only species A, because species A is the only species that has difference in concentration, and that's why it's gonna diffuse from the left hand side to the right hand side. This is the force or the first force that is a resultant of the first gradient or the first difference that we have here. The second force would be due to the density difference, which is what we call the bulk motion. And the bulk motion is just a motion of the whole mixture that has different density from the density of the other side. So this will create a force to make the density equal. So the motion will take place for the whole mixture that as a whole has a density different from the density of the other side. And that's why this bulk motion is not only affecting the species A, it's affecting species A and species B. And that's why I'm putting this in green and red for both of them, and I'm putting the diffusion motion only in red just to tell you that this is only affecting the red species or the red dots, which represent species A. So this is what happens. So if we take a look at Fick's law, you will see that the only driving force that was represented in this equation was the concentration difference, which represents or which tells us how much diffusion motion is taking place, and it never says anything about the bulk motion due to the difference in density. And that's why we are considering that the equation, or it's not we are considering, this is actually what's taking place, that the equation is only considering this diffusion motion, and it's not including the motion of the other components. And that's why the flux that is calculated from this equation is the flux with respect to the medium that is is around or the flux of the medium that is around it, and this is why the Fick's law is not considering all the forces, and that's why it's only calculating the flux relative to the average velocity. We can translate what we have discussed now into or in a mathematical form by revisiting Fick's law. So what we mentioned, that Fick's law is calculating the flux with respect to the average velocity, which is the total flux minus the average flux, which is this term Ca multiplied by Vaz is the total flux, and Vz is the average, Ca multiplied by Vz is the average flux, and we mentioned this before. This is the average velocity of flow. So either you can think of it this way, or you say this is the average velocity, or the velocity with respect to the average velocity, and multiply it by the concentration, then you're getting the flux with respect to the average velocity or the average flux. And now we can compare this to or equate this to the general form, which is the de Groof form of the Fick's law, the general form. Then the equation would be negative CdAb partial or dya dz. And then we can do some mathematics to rearrange the terms that we have here. And what we need to do is to get the actual flux, which is CAVAZ, and this is why we put it on the left-hand side, and we want to see what we have on the right-hand side. So this is the total flux, or the actual flux, that is the sum of the flux of the average of the diffusional, due to the diffusional forces and due to the bulk motion forces. And this is how we can represent it. There is one thing that we need to, again, understand well, is that the velocity of motion is not something that we can calculate, or we cannot, or it's not something that we can measure, because it's the velocity of some molecules diffusing in air or in water or whatever. So you'll not be looking into a tiny molecule that's going in space and to calculate its velocity. It's not possible, and that's why we want to get rid of any term that contains velocities, and we will start with this term. So CAVZ is or VZ, as we mentioned before, it's the average velocity, which is the summation of the C multiplied by V for each component divided by the total concentration, which takes this form in case of a binary system. So this is how the VZ is, and if you multiply it by CA as it's here, then it's going to be CA multiplied by C, which is the mole fraction, which is YA if we are in a gas phase. And then this is how the equation will look like. We can now substitute this instead of this, put it here. And the equation would be negative CdAb dya by dz, which is the first part, which is this. And this is plus Ca Vaz plus Cb Vbz. So now we got rid of the average velocity, which is a good point and a good thing that we can or a good step that we can take to reach a more usable form of the equation. And as we mentioned before, Ca multiplied by Vaz is the flux of the species A, which is the actual flux with respect to fixed point in space. So it's the actual flux, and these velocities are the actual velocities. So again, Ca Vaz and Cb Vbz are the fluxes of the components A and B relative to fixed z coordinates, and we can put them in the form of NAZ. And this is a new term that we haven't mentioned before. This is a flux. So we know that the flux used to be called as J, but now we give it another name, which is N, and N is the flux relative to fixed point in space, just to differentiate between the flux with respect to or relative to the average velocity and flux relative to the fixed coordinates. So this is NAZ and NBZ, which is C multiplied by V. So if we put n's instead of CV's, then the equation would be, as we see here, it's NA in the z direction equals negative CdAb dya by dz plus Ya multiplied by NAZ plus NBZ. And if you want to put it in a general form, then the equation would be, as you see here, it's nabla YA instead of dYA by dZ, in case you have the flux in X and Y and Z directions, and this is the total flux, and this is the total flux of A, and this is the total flux in B. So this is the final form of the equation, which represents the flux with respect to a fixed point in space. And we started with Fick's law and the definition of the flux with respect to the average velocity, and with some mathematics we were able to reach this form. This is a brilliant equation because it translates what we have just mentioned about the two forces that affect the flux, and we now can see these two forces in a form of a mathematical equation. The first force is the concentration gradient force, which is represented by this part of the equation, and this is how we see it. It's nabla YA. We have here the concentration gradient is the driving force, and this is what we can call the concentration gradient contribution to the total flux. And the other part of the equation, which represents the bulk motion or the flux due to the bulk flow, and we can call it the bulk motion contribution. And this is awesome because now you can see it by yourself, and the terms tell you, because this is NA plus NB is the total flux that you have. So this is how the total flux is affecting, or the bulk flow is affecting the flux of A, and this is how the concentration gradient is affecting the flux of A, which is very useful thing to see and to understand how these forces are represented in the form of two terms in one equation. So now we can apply the equation for molar flux, and we can apply as this form. It's gonna be N, uppercase N, and here you'd see concentration and mole fraction, and again uppercase N's. For mass flux, it's gonna be rho instead of C, and it's gonna be omega A instead of YA. It's gonna be lowercase n instead of uppercase n. So this is the main difference that you will see between these two equations. They are exactly the same, only the symbols that we're using, and this is what we agreed on before. The uppercase letters are for moles, and lowercase letters are for mass. And we can apply for any multi-component system, and in this case, instead of NA plus NB, it's going to be NA, NB, NC, and ND, and whatever the number of components that you have. So to summarize what we mentioned, this is an important, a very important table, because it tells a lot and it summarizes a lot of information in one place. And I believe this is important for the audiences, because I can imagine that many of you are already confused, because you have now many forms of the equation and you don't know when to use this and when to use this. So just to make it easy, just keep in mind that you have three cases or three parameters that are changing. One of them is either you're using mass units or mole units. So the equations that you have here are split into two halves, one for molar flux and one for mass flux. So if you consider that you are using molar flux, then you are choosing among 4 options, not 8. So this is cutting the number into half. So this is the what you can choose from, and this is one parameter. The other parameter is are you calculating the flux relative to stationary axis or relative to the average velocity. So if you are calculating the flux relative to stationary axis, then you are and you're using the molar units or molar flux, then you are choosing from only 2 equations. So you're cutting this into half again. So 4 after, so it was 8, then 4, then 2. And if you are operating at constant temperature and pressure, then the concentration will be constant. So you can use this equation, which is gradient of concentration, not gradient of mole fraction. So this is the equation that you will be using. So this is what you need to keep in mind. The equations that you see now give you all the alternatives and all the shapes of the equation, considering all the parameters or all the options. So you have equations that can be used for molar units and for mass units. You can find equations that can be used at constant temperature and pressure or at variable temperature and pressure. You can find equations that represent the flux relative to average velocity or stationary axis. So this is all, or these are all the options that you see. Again, this is important thing to notice or to keep in mind is the notations, the difference in the uppercase and lowercase, the rho and c and omega and y. These are things that you need to keep in mind. As I said, you will see them a lot, and you have to make sure that you understand what they represent. One thing that I believe you'll be thinking of is, okay, when will I know that I'm operating at or calculating the flux at with respect to relative to average velocity, or I'm calculating the flux relative to the stationary axis. This is something that we will discuss later, but just know for the time being that these are the options. You need to understand the differences, and once we reach this point, we will be discussing this in details, and we will see this slide again. So I want you to keep this in mind and understand the differences, and once we need them, we will recall it, and we will see why we are choosing whatever equation that we have from these. So that's all, and I'll see you in the next video, inshallah. Assalamu alaikum.